Hi everyone, this is the first in a series of videos where I'm going to go through and expand on some of the questions that caused a lot of you to have problems in the grade 11 chemistry review. I'm going to focus on the questions that I think are most applicable for this course, and they're mostly going to center around solution chemistry. I think this question with the net ionic equation is a great place to start because I talk a little bit about solution theory, and then we'll move into some of the quantitative and math skills. So this was question number 8, in which you were asked to write a net ionic equation. Excuse the sirens in the background if you can hear those. It just looks like a busy day in downtown London here. The net ionic equation, we have to start off with a few things first. So first of all, we have to complete this reaction and write a balanced molecular equation. But before we even do that, let's talk about what exactly is going on when we combine two aqueous solutions. So imagine in your mind's eye here, you have a beaker of aluminum chloride solution and a beaker of sodium hydroxide, and you mix them all together. Let's imagine them mixed together the moment before the reaction actually occurs. I want you to remember here what exactly aqueous means. That means dissolved in water. And for an ionic compound, when an ionic compound is dissolved, it is dissociated, okay? So the ions are apart from each other and they're just free floating in water, okay? So even though we write them as a single compound, those ions are all separated. Now, when you mix two aqueous ionic compounds, a reaction will only occur if there's a driving force. That's something about the products that is lower in energy or more stable than the reactants. Two types of products which are more stable are solids, because the lattice is lower in energy, or the gas products, which are smaller compounds which are lower in energy in a different way. In this case here, we want to see whether a solid is going to be produced. Let's first complete this double displacement reaction and see what the products are going to be, and then we'll see whether a solid is going to be produced or not. Okay, I've completed the equation, just writing a double displacement reaction, and I've also balanced the equation as well. That's going to be important, but I haven't written in the states of the products. So let's review how to use the solubility table. This table groups ionic compounds or combinations of cations and anions in terms of whether they are high solubility, as in if you have greater than 0.1 mole of that compound, will it stay dissolved in 1 liter of water? This isn't a very precise table, but it gives you a general idea that in most circumstances, compounds which have low solubility, if they're present in solution, they're going to come out of solution as a precipitate. Combinations of ions which have high solubility, when they're combined in solution, are going to remain in solution. So let's look at our products here. Aluminum hydroxide. I first start off on the hydroxide column right here, and then I see if aluminum is listed. I don't see aluminum in the exceptions, so that means aluminum falls under the most right here, which means aluminum hydroxide has low solubility. And if that's the case, we write an S for solid. We predict aluminum hydroxide would precipitate out of solution. My second product, sodium chloride. I find the chloride column, so I start with the anion. Then I look for sodium. I don't see sodium as an exception here, so sodium must fall under the most. You'll note here that all group 1 compounds, so any compound which has a group 1 metal, including hydrogen, has high solubility. So sodium chloride will not precipitate out of solution. Let's now represent that visually in terms of what we might see in a particle diagram. Okay, so here's the little particle diagram of my products. So what happens when we precipitate? The ions come together and they're held together, and we start to see a solid forming. More often than not, it forms at the bottom because it's more dense than the liquid for most ionic compounds. And then the other ions, well, even though we write it as a second product compound, the sodium and chloride are not connected in reality. They're just free ions floating around. So the point of showing this is the idea that a few of these ions were not at all involved in the chemical reaction. So the problem with a molecular equation is that it shows you a whole bunch of substances which are not involved in the chemical reaction. They are just spectators. So a net ionic equation will only show the chemical substances which are involved in the chemical change. So let's get rid of these particle diagrams and go through the steps. My first step to writing a net ionic equation is to start with the balanced molecular equation. So I've already done that. My second step is to take any substance which is aqueous and split it apart into ions. So let's start off here. We have AlCl3. So in every aluminum chloride, we have one aluminum 3+ ion, and then we have 3 chlorine 1- ions. Okay. Note that the subscripts, when we split up the ions, become coefficients because each chloride is not a Cl3. When the ions split apart, we have 3 individual chloride ions. So I'll do the same thing with sodium. And the same thing with hydroxide. Note that the 3 applies to both the sodium and hydroxide ions. Now, I always think it's better to split apart your equation into 2 lines if you're going to get squished at the end here. And I know I'm going to get squished. So I'm going to split this apart. AlOH3. Now, this was my precipitate. So those ions, in reality, are held together. So we're going to keep them together and write them together. Next up, we had our sodium ions and chloride ions. Remembering to apply the coefficient to both sets. So this equation here is called a total ionic equation. Ionic is as in I'm showing the ions, and total as in I'm showing all of the ions present. Next up, we are going to make this a net ionic equation. What I'm going to do is compare reactants to products and any chemical substance that is found in the same state, with the same charge, and in the same quantity. I'll cross off. So 3 chloride ions on the reactant side. I have 3 chloride ions on the product side. So even though they were present, there's no change there. So I'm going to get rid of them. Next up, 3 sodium ions on the reactant side, 3 sodium ions on the product side. No change there, so I'll cross those out. The aluminums and hydroxide on the reactant side are individual ions, but on the product side, they've come together to form a new substance. So I'm going to write those because there's a change there. So here is my net ionic equation. Aluminum 3 plus aqueous plus 3 hydroxides gives me aluminum hydroxide solid. So this is a more useful equation because it gets rid of all the extra stuff. It shows us what chemicals are involved in the change. And it's actually a more accurate representation of what's going on. This is a representation of the chemistry involved in a double displacement reaction. What we have up here is not a very accurate representation because it really shows a new compound forming when there's nothing happening with the sodium and chloride ions. Okay? So you're going to see a lot of net ionic equations moving forward in chemistry. So hopefully this is helpful for where those come from and what they mean.